Good? All right.
Good afternoon, everybody. It's the fourth group of today, and that's the quietest. All right. Good afternoon, everybody. Good afternoon. Very well done, very well done. Welcome to our 2017 Gen 7 Thesis Conference. I'm Professor Frank Cole, in the Director of the Gen 7 program, and I've had a great pleasure also being the mentor for this team for the past couple of years. So it's been a fun ride, right, guys?
Oh, yeah.
Yeah. So I think what you're going to be impressed with today is how much these students have learned. They jump into these projects with a grand idea and a grand plan, and those of you who have tried most anything in life, you know, it never really kind of turns out that way. We adjust, we modify, we review plans, plan A to plan B, plan B to plan C, and we end up with a whole bunch of knowledge. We have a whole lot of stuff we learn along the way. Sometimes the journey is different outcome than expected, but the journey is more than you talk about now. But I think you'll see that this group of students has done a whole lot of learning and has accomplished some really cool things. So how it's going to work is we're going to let them present for about 25 minutes. And then we're going to have a 10-minute time period for just questions from our discussants. Our discussants are distinguished scholars in the field. And I'm going to ask them to keep the questions kind of general for the first go around. Because after they've asked our 10 minutes of questions, we're going to open up the questions to the whole audience and ask whatever you want, anything, it's their game. And then the discussants and me and the team are going to sequester ourselves in the back room for the next hour and ask all kinds of other questions that aren't so general. So that's how it's going to work. Everybody good with that? All right, that's how it's going to go. Magnet, you ready?
Yes, sir.
Take it away.
Dr. Cole, is it recording?
It's recording.
Okay. All right. Hello, and thank you all for coming out to Team Magnet's thesis presentation. My name is Robin McFall, and presenting with me tonight are Thomas Ogden, Alex Johnson, and Nikhil Badami. Today, we are going to talk to you about magnetic field manipulation as a means of stabilization. Magnetic field manipulation is a form of non-mechanical energy transfer, meaning energy is shifted from one object to another without the need of physical contact. In this case, an object is lifted using magnetic levitation. We were inspired to research this topic because of its vast applications in the regulation of stability. By combining a microcontroller with magnetic levitation, we can make a stabilization system that both increases safety and prolongs the lifetime of the system itself. One future use for this technology would be using magnetic levitation for building stabilization during earthquakes. Other applications include vertical wind turbines and dynamic suspension systems. These applications have the potential to change the way we think about magnets. So what are magnets? Magnets are materials where the electrons are aligned to one axis of rotation, creating a net magnetic field. The field aligns differently based on the magnet shape. The top right image up here is a puck magnet, where the field is oriented so that the North Pole is on top and the South Pole is on the bottom. The bottom right image is of a ring magnet with the same orientation, North Pole being the top and South Pole being the bottom. The field lines shown loop around to connect the North to the South. It is the interaction between the fields of two or more magnets that causes like poles of magnets to repel and opposites to attract. A magnet and its field can be approximated using dipoles, which are represented mathematically by a small sphere approximated by an equation in polar coordinates. The shape of the magnets chosen for this project are very important. In order to achieve levitation, the fields have to be able to interact in the way that we want. A puck magnet is one of the simplest magnet shapes. The puck magnet is displayed on the far right. A ring magnet is a more complex shape than the puck magnet as shown on the left. With the puck magnet, the field is generated like a sphere on top and down below, but with the ring magnet, you get a much more complicated field as shown in the middle with that donut-like shape as it follows the magnet around the material that is present. That dip in the middle is very important because when we're trying to achieve levitation, that is the spot where the puck is going to best fit, and that will be explained later. Now, not all magnets are inherently magnetic material. A magnet can be made by using electricity as well. A solenoid is a passive two-terminal electrical component that resists changes in current. A solenoid can produce a magnetic field if a constant current run through the wire is wrapped around the ferric material like iron. The governing equation of a solenoid is Ampere's law. Ampere's law dictates how much magnetic field is produced based on the current forced through the wire. The size and strength of a solenoid's field is determined by the cross-sectional area, the length of the wire wrapped around the solenoid, the length of the solenoid itself, and its core material. Combining the concepts of permanent magnets with electromagnets, you arrive at the idea of magnetic stabilization. So what is magnetic stabilization? The property can be defined by Earnshaw's theorem, which, in its most general form, may be stated as no static charged body can be in stable equilibrium under the influence of electromagnetic forces alone. This concept is displayed in the GIF up on top. Basically, if the magnet on top is left alone, it will naturally want to flip over and connect with the base magnet, which is bad if you're trying to levitate. However, you can counteract this by creating a dynamic system, either by rotating the top magnet, as seen in the image on the right, or by manipulating the magnetic field through the use of electromagnets, which is the approach we have chosen for this project. When creating a magnetic levitation system, the magnets used must be carefully chosen. Not all pairs of magnets can be stably levitated. The forces generated between the two have to be strong enough to counteract the forces of gravity. So after researching all of these concepts, there were several research questions we set out to answer. The overarching question was, can we implement a microcontroller-powered, magnetically levitating system that can take user-defined displacements and achieve stability? Some of the other questions that we set out to answer that helped us with this overarching question were, what is the maximum recoverable disturbance we can achieve, and how long can we stably levitate? And now, here's Tom to discuss our methodology.
Thank you, Robin. So to get an accurate idea of how the magnets would perform in our prototype, we used a device that would measure the strength of each of the magnet's magnetic field at a specific height from the surface of each magnet. By taking these maps at a variety of different heights and compiling them together, we can get a good idea of how our magnets will work in the scenarios they will be facing during the prototyping stage. This real-world data will from this point on be called magnets. Map to data, excuse me. Here we see an example of the data we were able to compile. The X and the Y axes indicate the distance the measurement tool travels horizontally from a starting point, width and length respectively, and the Z axis indicates the magnetic field at that location. It should be noted that, as mentioned in the last slide, the height will remain the same in each measurement. For this measurement of the ring magnet, notice that the strength of the magnetic field increases in a ring corresponding to the shape of the magnet measured. The field also significantly decreases in the hole of the ring magnet. And here we see another similar graph, this time of our puck magnet at the surface of its top face. The magnetic field is much more uniform and easier to map. While having the map data is important, it is equally important to make sure that there are multiple ways for us to get the information that we need about each of our magnets and to check that our data is correct. To do this, we use the magnetic field simulation software. The virtual data would allow us to simulate what the fields would look like for our magnets, observe how our magnets would behave in a variety of situations, and make advanced models of our system and its interactions. This decision paid significant benefits. Here, we can see a graph generated from the simulation software for our ring magnet. The colors of this graph correspond to the strength of the magnetic field, and the lines correspond to its shape. As the colors get closer to red, as can be seen in the extremes of the magnet, here and here, the more intense the field. Meanwhile, areas in light blue on the opposite end of magnitude indicate areas of incredibly weak field strength. Notice the colors in the rectangle for the ring magnet viewed from the side. The center gets lighter because there is less magnetic material there. And here we have a similar virtual graph generated from the software that shows the magnetic field of our puck magnet. Note the darkening colors toward the rectangular end of the puck magnet viewed from the side. This is a good indicator of the strength of the field and the best location for using our equipment to the full effect for levitation purposes. At the end of the day, this virtual data is useful because it is more comprehensive than the mapped data and more easily produced. However, it is only helpful if it is able to accurately represent the behavior of the magnets. Because of this, we conducted a brief analysis of our simulation data compared to our map data to see if there was reasonable agreement. Here, we have a graph indicating the strength of the magnetic field of the ring magnet, which is displayed on the y-axis, as the distance from its surface increases radially, which is measured along the x-axis. Notice that it matches very well with the simulation data overall, and that material 1 and material 2 in particular match its mapped behavior. We decided from this visual analysis that the simulation data would be valid to map the puck magnet for these ceramic materials. The puck magnet, on the other hand, did not fare so well. Again, we have magnetic field strength in the y-axis and radial distance from the surface on the x. The general shape of our blue mapped data doesn't exactly match with the general shape of the simulated data. Even worse, no one material lines up with the line. It can be noted, however, that a combination of two of these materials would produce a similar field to the mapped data. Unfortunately, the software only allows the mapping of a uniform material. So from all this research, what did we learn? We were able to determine the ideal material for our magnets so that they could be purchased and prepared by the prototyping stage. We learned the software would work for some magnets, such as our ring magnet, and we learned that the virtual data didn't agree with our map data for the puck magnet, forcing us to use only the map data for its modeling. This information will help a lot in creating a model for the next few steps. Lastly, we learned that the software had difficulty in mapping two magnets in close proximity, an integral part of our project. In the future, an alternative software with this capability, as well as the capability to map magnets made up of multiple materials like the puck magnet, could benefit research groups continuing on our work. Now, I'd like to pass it off to Alex so he can elaborate on our prototyping processes and control algorithm derived from these data.
Thank you, Tom. Hello, so I'm going to talk about the next steps in the magnet data analysis and how we use that to design our control algorithm. And the first step towards deriving our control algorithm was to be able to take a measurement of the magnetic field of the puck magnet and to solve an equation to find its radial position. And ideally, we would do this by taking a measurement of B puck, shown in the quadratic up here. Shown in the quadratic up here. Ooh. Here we go. Sorry about that. So this is the quadratic equation describing the field of the puck magnet. And ideally, we would take a measurement of the magnetic field and solve for an R, which is the radial position. But because of the proximity of our sensors to the solenoids, we have to filter out the effect of the magnetic fields of the solenoids, which is unfortunately a function of the current and is variable in time. So that amounts to taking a magnetic field measurement and solving this quadratic, where this is the magnetic field of the solenoids, B solenoid I, as a function of current. So what we need to do that is to get an expression of the magnetic field of the solenoid as a function of current. To do that, we begin with the Biot-Savart law, which essentially tells you the shape of a magnetic field for a given current, an element of current. And we can use that to get the magnetic field expression for a current loop. And then we can essentially integrate that across the length of our solenoids to come up with an expression for the magnetic field of our solenoids. And what we'll get is a linear equation with respect to current, shown here. Each of these equations is the longitudinal and radial components of the magnetic field, shown in the diagram here. So By would be the longitudinal component, and B solenoid R would be the radial component. Those constants just come from an integration of the equation above. So we can use these equations to, knowing the current and knowing the measured magnetic field, filter out the field from the solenoids, measure only the field of the puck magnet, and solve for its position. So after we've given ourselves the ability to take a measurement and determine the position of the puck, which is our observation, we need to actually control it. We need to have an input. And so the first thing we need when making the control algorithm is a differential equation, which essentially just tells us how the puck wants to move. And what's really important for our level of knowledge is that preferably the differential equation is linear. So to make the expression for how the puck wants to move a linear expression, meaning it's just a line, well, the differential equation is a line, we treated the puck magnet as a dipole, and we used a Taylor series approximation of the solenoid's field, which we think is valid for small radial displacement. This expression is the force of the ring magnet on puck. U mag is just the magnitude of the dipole vector of the puck, and the constant A right here is just it's a compression of a bunch of parameters of the ring magnet. The expression on the right, 2U mag times ICD over M, is the force, or the acceleration experienced from the force of the solenoid, which U mag is the same, M is the mass of the puck magnet, and C is also a constant related to properties of the solenoid. So given that differential equation, we can create a compensator, shown here, H of S, which essentially tells us how to create an output given a certain observation of input. And it relates radial position to an output current. And we can essentially use this to come up with constants that actually allow us to calculate an output current given an observational position. And so given that we have the control algorithm, the next step is to actually make the solenoids, which are how we're creating an output. And so we decided to custom make our solenoids because we wanted to control specific parameters that we thought were important and that we couldn't necessarily choose from essentially catalog shopping. However, by making them ourselves, we essentially guaranteed that we would build in errors to the system, and so that the solenoids would require calibration to make sure they work properly. And so our solenoids use 24 gauge magnet wire wrapped around a ferromagnetic core, which is just not a screw. And it was 9 wraps deep and 30 wraps long, which is 270 total wraps. This is the results of the calibration of the solenoids, where we essentially measured their output given a certain input current. And we started from 0 current and worked our way up to 1 amp in increments of 0.1 amps. As is shown, solenoids 2, 3, and 4, which is the red, the blue, and the green, which is hidden behind the blue kind of, but you can see that. They all worked about the same, which means that they were constructed properly. However, solenoid 1, which is the black line shown above, had a different output, which means there was a problem in its construction. And so we would need to recreate that solenoid to get the performance we need. And now I'll have Nikhil come up to talk about the circuit that we used to create the inputs to the solenoids.
Thank you, Alex. The most important requirements for our driving circuit were a rapid response time, simplistic design, the ability to run on a small output from our microcontroller, and the ability to run in parallel. We designed and tested 2 separate circuits in order to ensure that the power draw nor the response time would cause our system to fail. The first circuit was a BJT self-contained Darlington pair current amplifier, which allowed us to amplify the low-level milliampere output from our microcontroller to full ampere values that would then be useful to our electromagnets. The other circuit we designed was a more typical MOSFET switching circuit. Both circuits passed our preliminary tests and were ready to be implemented and compared in our full system testing. We also needed to program a microcontroller to act as the brain of our apparatus. We originally decided to use interrupts, which are prioritized signals connected directly to the CPU that alert to tasks that need immediate attention. Interrupts allow the programmer immense control over the microcontroller's hardware. However, the precision they provided proved unnecessary for this project. The team decided that a simple control loop would be ideal for this application. The control loop would read in data and then process it using an algorithm that we developed. The code would then cause the microcontroller to rest for approximately 25 milliseconds, thus forcing the code to run at 40 hertz. We also needed a custom-made platform to support our ring magnets and solenoids. The completed platform is shown here in the picture on the right. Aluminum was used because it is a durable, non-ferromagnetic material that would have a negligible impact on the magnetic field from our ring magnet. The platform was fabricated out of 3 distinct pieces cut from 1 slab of aluminum, with the bottom piece being left unprocessed so as to act as a base. 4 squares were welded to the bottom piece so the ring magnet could be propped up to allow the passage of wires underneath. 4 small holes were also drilled into the center to allow us to secure our solenoids in place. We also needed a way to mount our sensors and connect them to our microcontroller. We accomplished this by creating a cross out of 2 pieces of PCB, otherwise known as printed circuit board, and a third piece that was added on as a shelf. The 3 pieces were cut and oriented in an XYZ coordinate plane. The Hall effect sensors would then be soldered onto the individual pieces of PCB. In this orientation, we would be able to detect changes in our magnetic field in all 3 directions. We were able to get preliminary data regarding our Hall effect probes by using this cross and soldering sensors onto it. While we were able to mount some sensors to our cross, the sensors were too small to line up with the holes on the board, which made it difficult to solder wires to it and connect them to our microcontroller. We decided that etching a proper PCB would be the best way for us to move forward with our project. The schematic and part models we created in Eagle will prove invaluable to future research teams attempting to further our work. In conclusion, we originally started our project with the intention of making a microcontroller-powered magnetic levitation system, but later expanded our idea to a general theme of stability. The results we were able to produce will prove invaluable for teams aiming to further our work. The magnetic maps we created will help future research teams quickly choose workable magnetic pairings for the ring and puck magnet. Additionally, the algorithm we created will save future research teams an immense amount of development time. We also believe that our work has great potential for further expansion and further investigation. We believe that future teams can attempt to implement user controls and also attempt to apply this technology to wind turbines or shock absorption. We would like to thank the following people for their contribution to our work: our mentor, Dr. Frank Cole; Emma Holmes, our former teammate; Dr. Kristen Skendel; Dr. Vicky Hill; Leah Tobin and Jessica Lee; our librarians; all the faculty members who helped us further our research; our Launch UMD donors; and of course, our discussants. That concludes our presentation. We will now open the floor to questions.
Good job, folks. As promised, we're going to take about 10 minutes and have our discussions and ask questions of the team, and then we'll open up everybody else. So if you think of the questions you want to ask, we can turn comments, and we'll let anybody discuss it. I think I saw the spark in there. There you are. Anybody can go first. I asked what you do though, and just introduce yourself briefly so they all know why you're here.
Yes, so I'm Dan Layford, professor of physics and geology, and so I understand there's a ring magnet, there's a puck, there's 4 solenoids, and then there's a Hall 3D sensor. Where were they intended to be relative to each other? What was going to be the shape of this thing overall?
Okay, so the question was the relative positions for the forming series of components, the ring magnet, Hall effect sensors, electromagnets, and puck was left a little ambiguous, so we're going to clear that up. I'll just take this question. We'll leave it. The ring magnet and the electromagnets are in plane with each other at the base. And then inside the base, centered, the Hall effect sensors are incredibly small. And actually, if we go back a couple slides, let me find. This shelf fits in, so the height of that shelf is mainly to accommodate the electromagnets that fit in all 4 corners of it. So that shelf is directly located over top of one of the electromagnets, and the overall product, the base is about 1.5 to 2 inches tall. That's including the electromagnets, the ring magnet, and the Hall effect sensors. Now, the puck is levitating about 0.7 inches above this apparatus and stabilized, ideally.
Okay, so let me make sure that I understand the suggestions. I've got a ring magnet, I got a pump right on top of it, I've got Hall sensors right below, I think.
The ring, electromagnet, and Hall magnets are all in one plane, or Hall effect sensors.
So the solenoids that are like pointing toward the ring magnet?
The ring magnet, we use the whole of the ring magnet to fit in the 4 electromagnets vertically.
Oh, okay, so
Yeah.
they're like that?
Yes.
Okay, and then the ring.
The ring is around it, and the Hall effect fits in with the electromagnets. Sorry, that was confusing. Yes. So we were especially constrained space-wise when creating the electromagnets, because all of them had to fit inside a 1.75 diameter, diameter of the ring magnet. So I believe our calculations led to about 0.6 inches was the maximum possible size, width of the electromagnets. So we had to, that's why we originally reached out to custom design of the solenoids.
Okay, now we all have a visual image of what this thing's going to look like.
Do we have the
Another question?
sample?
Hi, I'm Elizabeth Snell, I'm professor of mechanical engineering. So as was pointed out in the introduction, this was clearly a project in which the journey touched a lot. So what did you primarily learn from this experience? Not talking about this like very potential of the building, but what did you actually learn from the project?
So the question was, what did we pick up along the way besides what directly related to what's in our presentation? I'll start this off, and I'll invite any teammate to come up after me to add on. But we started out a very different topic. We were originally Team Maglev, and we were working with trains and electromagnetic propulsion for trains. So we carried on the theme of magnetism because we had done a large amount of literature review in that field, and all of us thought it was honestly really cool. So we moved on from there, and our different disciplines all came in, and we realized a way to hit things like aerospace control theory with that, EE, CompE, circuit design, and mechanical engineering, and civil engineering, and physics all blended in to give us what we have right now. The things that I feel most valuable was putting to use what I had learned in the classroom. So circuit design in the classroom was often a canned lab situation where you are given, this is a schematic, here, make it. But when you have to create your own schematic, it is a much different experience, and especially product design led into this, so we had to physically be able to put everything together and fit it together, which we did get a first prototype done. We couldn't demonstrate today. It was deconstructed to be used in the second prototype, which was a long process. So that's what I picked up the most. I'd like to invite anyone else.
So a little bit additionally, you can see there's a lot of us here. There are 13 of us with 8 different majors. We bring a lot of different things to the table, each of us, and so I think one of the valuable things I took out of it was being able to balance different ideas and work in a huge team towards one common goal and kind of work together like that. Anyone else, guys?
Anybody else want to contribute?
So what I mainly learned was the difficulty of fine-tuning a physical system, especially when it involves something like magnets, which is something not most of us specialize in. So I did a lot of the programming for the actual microcontroller. So I definitely learned that it can be a long and arduous process to have such a big team work towards one goal of getting a magnet to levitate in like a system that really should, in theory, work with the correct variables, but in practice is much more difficult to construct.
Very good. Let's move on to another question from another discussant.
Rob Sander, aerospace engineering. So I'm focused on the control part of it. Students are really at me. So the question is, the control algorithm you designed is measuring R and varying I through the solenoids, current through the solenoids, correct? Yeah. So I guess my question in all that was, can you really understand a better picture of the overall geometry that was envisioned for this thing when it went to full closed loop? What was R? Is that the radial offset from the center of the ring?
So the question was, in our control theory, if I can find the slide real quick. So in this and the prior slide,
I see next step, but not R. In that previous figure.
the R offset, okay. So this diagram is tilted to the side. If you were to orient this loop here as the plane, the top plane of the base, so this is where the Hall sensors are. They're all going to lie in this plane.
So that's the radius of the
Yes.
ring?
So this Y offset here is the 0.7 inches ideal levitation height, and the R offset would be how far divergent from the center, what eccentricity do we have to then account for and recenter with.
So you had a 3-axis set of Hall sensors that was trying to measure that?
Yes,
That offset R?
yes.
How far did you get along the path of actually successfully recovering R from the Hall sensor measurements?
We calibrated, in our original prototype, we had X and Y, and we opted to not take care of Z at the moment because Z should be fairly static, and if there is fluctuation, I'm saying Z as in distance away from the, yes, so Y. So we have X and Z, and we decided to not take care of Y because if we have any variation from there, it's honestly near impossible to create that variation other than an earthquake or bouncing motion. The easiest offset is to slide out of the saddle point that it wants to sit in. So in the X and Z, we had a running system up on a screen we could display. We were calibrating from bits, 0 to 1023, I think was our original bit count. And we were calibrating from bits into inches offset. And we were in that process when we thought we could quickly implement a prototype 2, which, no. It went a little sideways at that point.
That kind of answers my final question, which is how close did you actually get to closing the loop on this?
With a magnet, we could see all of the displacement. We could see an R that was roughly calibrated, but we did not have a point where we could let go of the magnet and have it levitate.
Very good. Other discussion questions?
Discuss it. Discuss it first, please.
Elizabeth Mellon. So the audience may have heard about levitating frogs. Can you explain how that works?
The question was, there is a demonstration that has recently been done to levitate a frog without harming the frog, even though a frog is not an inherently magnetic object or ferromagnetic in almost any sense. Do we have? I believe Alex wants to.
I think hopefully I answer it right. It's depending on the strength of the field opposing the object, you can align the atoms and you can align the spin of the electrons on the atoms of the material and essentially force it to be magnetic. Yeah, and there's specific parameters that define if it retains its magnetic properties afterwards, etc. But that's, I think, what's happening.
I'll actually add on to this one. This is a very similar process to an MRI, actually, where you can flip the water atoms in the body in order to observe the rate that they switch back and forth. And MRIs cause no harm, no pain. Unless you have a metal implant, you should not use an MRI. But we can take images of the rate, the frequency at which the water atoms flip, and that is imposing a false magnetic field on the body, and then that dissipates quickly, at least in the MRI case.
All right, we're going to open the question to everybody, but it includes discussants as well. I'm going to give a great anxious question behind you here.
I was just curious, you were going solenoid and magnet. Couldn't you just go some kind of magnet or solenoid amplifying magnet to metal, or are you just doing both so it's more powerful?
The question was why use the combination of permanent magnets and electromagnets? The short version of this is that with permanent magnets, you can never have a varying magnetic field unless you are also moving the permanent magnets. And we wanted to have a physically stationary device. So by introducing electromagnets, we are able to create a non-static parameter through the electromagnets that can then create stability, because Earnshaw's law dictates that static elements cannot levitate each other stably.
Thank you. Other questions about frogs or other things?
So I like the magnetic field maps. Those were very nice. You had some sort of scanner, I guess, over which then you flew a whole probe or some other ones. What was that scanner? I didn't notice.
Let me pull it up real quick.
It was an object you found, not built from scratch, I guess.
Yes, actually, our original mentor, Dr. Gomez, allowed us to borrow his lab. This is the scanning system. Here is our puck magnet, and this probe right here on the end, actually, I believe on this end, is the Hall effect sensor that is scanning, and you have 3 servos, servo motors attached to a processing system that increments at incredibly small steps, pulls the data, adds it to an Excel sheet, and captures the whole scan at various heights.
But was this a commercial device? Or a
No,
Professor Gomez?
this was Professor Gomez special.
Other questions? Come on, ask me questions. Yes.
Combination of 4 total years. Is this the combination of work of 4 total years of work, or is it like 1 year of just getting to know each other?
So this is a question about the timescale of Gemstone, the Gemstone process. I'll try and answer this as short as possible. There's a lot of Gemstone that we've done. So freshman year, we all start out not knowing anyone that came in, or maybe one person from our high school, and all of the projects are proposed by the spring of freshman year, and teams are formed. Over that summer, the literature review is performed, and you get to know your team. That fall is really the first team bonding experience that you have, and jump into kind of the nitty-gritty of it. In that fall, that is when we switched our original project plan. We also switched our project plan that winter, and modified heavily in that spring. Coming into the summer between sophomore and junior year, you are to collect data, build prototypes, whatever fits your team best, and form a solid methodology like we discussed earlier. And then by the fall of senior year, you should be done with that process and starting to write your thesis. And we went over a little bit on the done with that process. We continued on into January for making it work with what we got. And we wrote our thesis in the past couple months and are generally satisfied with where we sit now.
Other questions? Yes, sir.
So I built Blankenship engineering. I want to compliment you on the work you did on characterizing materials, circuits, and the like. It was very impressive. That I know you had trouble building a prototype that functioned. Sort of disappointing. You pointed out early in yours, at some point in your thesis, that it's much easier to stabilize a spinning body. Did you try that?
The question was, would it be easier to stabilize a spinning body versus have a physically static and stabilize via electromagnetism? Yes, we considered that. We actually had a prototype. We bought a toy to sample, a little tabletop. You spin a top that has a magnetic disc in it, and you raise the disc and lower the disc, and hopefully it stays in the center. Actually very hard to get going, and we realized that this physical instability, even the slightest of breezes, could knock it out of place. And you are limited to approximately 15 grams, at least in the model that we had, and we wanted to be able to expand our product or our prototype into heavier objects in order to make it more useful, because there's only so much you can do with a 15-gram maximum, and that's assuming 7 or 8 of those grams are the magnet that's keeping it stabilized. So you have about a 7 to 8 gram payload that you could do tests or whatever you needed this object for. So that's why we went down the route of electromagnetic stabilization as opposed to physical spin-stabilized magnetic levitation.
Any other questions to wrap up this session? No? Well, I'm going to start with a big round of applause from the whole group for Team Magnet. So what's going to happen now is the team and the discussants, Daniel will lead them back to the room. I will catch up with you as soon as I can, so don't start too fast without me. You guys can make your way out of the room, gather all your stuff, stop being formal, get your umbrellas and directions, and make your way down the hallway. They're going to spend the next hour kind of fun with us. And we are now setting up a buffet reception outside. So you have an hour to kill till they're back. So enjoy some snacks with the posters, and we'll see you in an hour. Thanks for coming.